Well, hello everybody. Welcome to Blue Marble Science. How stupid can you be? Well, I'll tell you what, Mitchell from Australia just loves that challenge. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors back out of punching range, and let's light this dumpster fire and have some fun. This is what we call a scalene obtuse triangle. It's a triangle where none of the sides are equal length and none of the angles are 90 degrees. And this one is obtuse because one of the angles is clearly greater than 90 degrees. Now we can always take one of these triangles and make two right triangles out of it.
Oh, there's the right angle triangle. Had to put it in there. Had to put the dirty little secret in there. You still need a right angle to work out the Pythagoras theorem of this. Yeah, it's all derived from Pythagoras theorem from right angle triangles. Can't get away from that fact. Yeah, just got to put the dirty little secret in there. Don't you, Blue Marble Science? Yeah, even though it's an obtuse triangle. You're still going to need 90 degrees or something in there, mate. Something that you can't achieve on a globe. But let's continue.
No, Mitchell, I carefully explained to you in the previous video that we don't need the Pythagorean theorem to work out all the details of this triangle. All we need is the law of sines. And using the law of sines, we can get the lengths of all three of the sides, and we already know all three of the angles. You just weren't paying attention. Just as I show there, but that's not the only way to solve the problem. What if we know this? What if we know all the angles and the length of one of the sides? Well, let's identify some points. First of all, that's the location of the satellite. That is the center of the Earth, and that is a position on the surface of the Earth, in this case, Perth, Australia. We know that.
And can I just point out that they know the inherent properties of a triangle are three straight lines. Can you see any curved lines there? No, it's definitely no curved lines. Something that they know they need to work out triangulation. Something that is not achievable on the globe. When looking through a sextant out at the horizon, obviously there's no horizon here, it's just beautiful scenery. But when looking through a sextant to the horizon, what are we looking at on your globe? Is it a refracted horizon or is it geometric?
Atmospheric refraction is accounted for in the correction table for dip of the horizon. The dip correction compensates for the fact that observations made by a navigator through a sextant are not performed on the level of the horizon. The difference between the visible horizon, the line where the sky meets the sea, and the geoidal horizon, the plane perpendicular to the zenith line and the location of the observer, is called dip of the horizon. This dip of the horizon is not only caused by the elevation of the observer's eye above the plane of the geoidal horizon, but also by atmospheric refraction. These equations are empirical and include the effect of the curvature of the Earth as well as the effect of the atmospheric refraction on the dip of the horizon. And all of that is included in the correction table. Maybe you should look into this stuff, Mitchell, before you try talking about it.
They flip-flop between the two to suit themselves. It's geometric when they want to hide things. But when we say that there is no geometric horizon, that the black swan proves that we do not have physical Earth curvature, they then go back to it's refracted. And that absolutely debunks the notion of not only a curved physical edge for things to get blocked by, but also you cannot use a sextant to look at the horizon. What are you looking at when you're looking through the sextant at a refracted horizon? A bendy line? One of these lines being bent? You can't even use this triangle because you need a 90 degree, which is just shown needs to be in there, because that's this dot here's the surface of the Earth. This dot here is what he was trying to measure, the geostationary satellite. And this dot here is just the made up point in the center of the Earth, which he doesn't want to put in here because of the necessity to have R in the first place. You're going to see that in a second. All right, let's keep going.
Declination from the satellite to Perth is 5.05 degrees. We know the latitude of Perth, and that's 31.95 degrees. And those two sum to 37 degrees, meaning that the third angle has to be 143 degrees.
And what is 143 degrees, this angle? What's that representing? From the angle that you're trying to shoot here to the geostationary satellite to where? The center of your presupposed spherical Earth? Yeah, you're going to need R for that. Let's continue.
Are you with me so far?
Are we understanding each other?
We know one other thing. We know the radius of the Earth.
There it
The
is.
radius is 6,357 kilometers. And that's not a supposition. That is knowledge we've had for more than 2,000 years fairly accurately and very accurately for hundreds of years now.
Well, this is pretty awkward. You're going to need to tell Mr. Sensible.
Best, you would have disproved the radius of the Earth.
Oh, man, this is so awkward. Blue Marble Science just said that we have known the radius of the Earth for over 2,000 years. Somebody forgot to tell Mr. Sensible. Yeah? Because at best, what's happened?
At best, you would have disproved the radius of the Earth.
Ah, this is awkward. This is very awkward. It'll be even more awkward if one of the guys in your video, Where's Wally, would say something like this.
But you're going to need half of that.
You're going to need half of that? Yeah, Where's Wally?
This is as far as Mitchell gets in his attempted debunk of my previous video, because as soon as I say what the radius of the Earth is, and this is known, it's measured, we have known it very, very accurately for hundreds of years now, Mitchell simply repeats what he's been told to say by the likes of Nathan Oakley and Quantum Eraser. Those two idiots have convinced poor Mitchell that somehow or the other they have used this picture to prove the Earth doesn't have a radius. Have a look at this highly distorted, highly refracted screenshot from a video of two oil rigs off the California coastline. Now, Mitchell, this is not how we measure the radius of the Earth. We don't go to the beach crawling around on our hands and knees staring at the horizon to try to figure out what the radius of the Earth is. That's not how it works. Of course, the picture they don't want you to see is this one. It's those same two oil rigs, but taken on a normal day when you don't have a lot of distortion and a lot of refraction. And there's a real problem here, Mitchell. That horizon cannot be in front of those oil rigs if the Earth is flat. That is impossible. And you have no answer for it because Oakley has no answer for it. But that's not the purpose of this video. Let's move on into something that is really astounding.
Is Polaris. Another flat Earth proof. Well, let's look at this beautiful image that I put on my thumbnail today. If you missed it, here it is. This beautiful image in the middle there, that's Polaris, Star Trail of Polaris. And this is from somewhere in Indonesia, south of the equator. That's right, seeing Polaris south of the equator, 8 degrees south, yeah, of the equator. Now, not only does this prove that it is not just the north that can see Polaris, you can definitely see it south. This is 8 degrees. And I'm sure there are more images like this. Even further south, seeing Polaris. Now I'll bring up the website so you guys can go and have a look for yourself. It's from blamethemonkey.com. There we go. It's just detailing. So if you can see the North Star in your shot, then you should be able to get the rotational effect in your photo. Most people have to settle on just calling the celestial pole the Polaris. In the shot below, I have carefully calculated the position of the celestial pole before visiting this spot in Indonesia. Luckily, I had a crystal clear sky the entire night. I was able to capture the celestial pole in all its glory. Obviously, the unique landscape helps as well. Yeah, beautiful image. Thank you. The stars dance above the extraordinary Mount Bromo, Indonesia, as the morning fog rolls through the... Yep, beautiful. Isn't it? There's Polaris, 8 degrees below the equator. Now, this isn't the killer blow here. This is just an observation. What we extrapolate out from this is great. So, because we know each 1 degree that we measure from Polaris is 69 miles, yeah, something that the globe believers are punting as globe proof. So the location is 8 degrees south longitude. So it's 98 degrees from this location to Polaris. Now they say that they've gone over a curve. Yeah, that south of the equator, there's a bulge between them and Polaris, so they can't. It's Polaris right there. They can see Polaris. There's no bulge. Yeah, they're not 8 degrees over a bulge of the equator. No, it is a flat Earth. So to extrapolate that out, when we're seeing Polaris at 98 degrees from our position, 98 times 69 miles from the observer to the GP of Polaris, which has to be an absolute straight flat measurement, is 6,762 miles to the GP of Polaris from the observer. 6,762 miles of absolute flatness right there.
Mitchell, how sure are you that that's Polaris? You're going to look pretty silly if it's not.
So that's the GP of Polaris right there. And someone's looking at Polaris, you know, when you're looking out the horizon, to get that baseline measurement, even if you're up high, to do the dip correction, you still extrapolate out how far off the flat surface you are. That is what dip correction is. You need the dip correction. Flat surface of 6,762 miles. Now, I kind of gave away the game right here. I kind of moved it over. Look at this. What is the radius of your globe believers? 3959 miles. How can we, because this distance here, that is a flat radius to get the area of equal altitude. A flat radius of 6,762 miles, absolutely flat. How can that fit into a globe of 3959 miles radius?
Mitchell, the distance is measured over the surface of the Earth, not tangent to it. Come on, man, this is getting embarrassing.
Yeah? This is one of the killer blows right here, but it gets worse. There are some globe believers that like to double down on Polaris being a globe proof and a flat Earth killer. Yeah? How does this radius here, 3959 miles, yeah, that is the extremity from the center of their presupposed spherical Earth to the edge of their presupposed spherical Earth, the radius, yeah? How does an area of flat, level ground fit, of 6,762 miles, fit on anywhere that has the physical extremities of 3,059 miles, 3959 miles? It does not work on a globe, that image that we just saw, Polaris.
Are we understanding each other? You're an idiot!
Polaris being visible 8 degrees below south of the equator, 98 degrees from the observer point to Polaris, does not work on a globe. Yeah, they have to think that they're on a curved surface. So let's just put this area of equal altitude up. So we've got the radius, the flat radius, not to a presupposed spherical Earth, no, because their radius only goes to 3959 miles, which is nowhere near this. So this is the area of equal altitude. So looking at Polaris, 8 degrees below the equator, 8 degrees south of the equator. When we can see Polaris, we know we can extrapolate out a distance to its GP point, absolutely flat, of 6,762 miles. Yep, this is the circle of equal altitude that we use. No, Adam Meakin, is 98 degrees on a ball? Absolutely not. This photo here, someone has definitely seen Polaris from 98 degrees. Yeah? 8 degrees south of the equator, 98 degrees to Polaris. Whew, that's quite a distance. What is it? 6,762 miles of absolute flatness in this image right here. That's what we can extrapolate out. Because we have got an angle, because we know the GP point, because we know it's absolutely flat from the observer to the GP point of Polaris, 6,762 miles away, yeah? This is why Polaris absolutely proves a flat Earth. It is beautiful, isn't it? This image here, Polaris, 8 degrees south of the equator, 98 degrees from the observer to Polaris. A flat distance, straight line of 6,762 miles. This is why Polaris absolutely proves a flat Earth. It is a flat Earth proof. It is beautiful, isn't it? Whew. That was quite a presentation. Hope you liked that, Dr. Bob. Hope you liked the Blue Bumble Science. Hope you liked it, Wally. It was good fun.
Well, while you've been busy doing some extrapolating, I've been doing some extrapolating of my own. And this next part is going to be a lot of fun. You managed to find a photograph of the northern celestial pole taken from 8 degrees south of the equator. That is truly remarkable, Mitchell. That's a beautiful picture, is it not? I'll tell you what, the words are a little small, so let me blow those up. We want to read this. What is the celestial pole? The celestial pole is as easy to explain as the celestial equator because it is based on the axis of the Earth's rotation. So essentially, if you face north or south, you'll end up seeing the center of the Earth's rotation in your frame. There's a bit more complexity to finding the exact location and elevation of the pole, but that's the simple explanation. Now pay attention to this part, Mitchell. Something else to keep in mind is that regardless of north or south, many people call this the Polaris. Let me say that again. Many people call this the Polaris. And that's due to the fact that the star Polaris, commonly known as the North Star, is only a few degrees off the center of the rotation. So if you can see the North Star in your shot, then you should be able to get the rotational effect in your photo. Most people have settled on just calling the celestial pole the Polaris. Are you keeping up here, Mitchell? What the guy just told you is it could be either pole. People just refer to it as the Polaris. So let's continue. In the shot below, I had carefully calculated the position of the celestial pole before visiting this spot in Indonesia. Luckily, I had a crystal clear sky the entire night, and I was able to capture the celestial pole in all its glory. Obviously, the unique landscape helped as well. Well, I'll give him that. That landscape is very unique. There's that picture again. And the caption at the bottom simply says, "The stars dance above the extraordinary Mount Bromo, Indonesia, as the morning fog rolls in through the caldera." Well, that's a volcano in Indonesia, Mitchell. Have a look at those very distinct features. You see a rather high mountain in the background. In the foreground, you see a rather large crater and a protuberance coming up from the floor of the caldera. That's a screenshot taken from Google Earth. I took a wild guess at the approximate location of the photographer for that photograph because he didn't actually specifically identify where he was. But there's the photograph, and there's a screenshot from Google Earth. They look remarkably the same, don't they? But I want you to notice something about this Google Earth screenshot, Mitchell. Notice what direction north is. North is behind us. In this view, we are facing due south. So let's see, does it match? Well, I'd say that matches pretty well. Let's try it again. There you go. That Google Earth screen capture does a pretty good job of matching the actual photograph, despite the fact that I don't know exactly where the photographer was at the time he took the picture.
That was nice, that, wasn't it?
So Mitchell, that's not Polaris. That's the southern pole. This picture was made from the north rim of the caldera facing south. This pole can't exist on a flat Earth, Mitchell. But it does have a name, Mitchell. It's called Polaris Australis. How about that? Oh, thanks, Wally. Welcome to the globe. And oh, by the way, I asked you a couple of questions in the last video which you ignored. I asked you if you could see Polaris from Australia, and the answer to that is, of course, you cannot. And I asked you why not. You didn't answer either one of those questions. All right, let's move on to a different question. Do you now understand why a sextant can't work on a flat Earth, Mitchell? Give it some thought. I'm sure you can come up with something. Hey, thanks for watching. Hope you guys enjoyed it. Don't forget to hit the like and subscribe buttons down there. Click the little bell if you like notifications. Shout out to the patrons and PayPals. I really appreciate everything you guys do. And with that, we'll see you guys on the next one.